So the topic which we're gonna see today is convolution neural network, and this is a very important chapter if we want to work on a computer vision problem, mainly classifications and object detections. Before this, we covered feed-forward network, and there the key concept that we learned was every neuron was connected to every other neuron of subsequent layer, right? Now that neural network is perfect, but it's not very much suitable for image detection kind of problem. Okay, mainly there are two reasons for that. One is something called gradient vanishing problem. So what happens in case of deep neural network is we are having a lot of learning parameters, right? We had lots of W's, we had lots of P's. So there's a problem called overfitting. So what that overfitting is, let me first of all cover what overfitting is. So whenever we are training something, or you can think from a real life perspective also, what happens is if we have to learn something, if we learn too hard on any specific subject, instead of understanding it, with sometimes we try to remember it, we mug up the thing sometimes instead of understanding the concept, right? So this is called an overfitting problem. So what happens in case of neural network is, instead of understanding or generalizing the functions, it tries to remember that specific function. So in real life situations, with when any data comes which is unseen to the model, it performs really poor on those data. It does well in case of training data, but when it comes about the new data, unseen data, it doesn't perform well. This problem is called overfitting.
But test data is always unseen data, right, Ashutosh? So why we say it's overfitting when, in any case, even in the regular neural network,
Mm-hmm.
we always have this data which is test data, which is unseen, which it
Yes,
doesn't know.
correct. Yeah,
So how is
but
it different from what you are saying?
uh, yes. So see, we do have test data while validating the performance of model, but we always do the training of our neural network on training data. So
Yeah.
what will happen if we use a too many number of layers, too many number of neurons, instead of generalizing the pattern in your training data, it will try to mug up, right? Let me explain you graphically, right? So if suppose this is my pattern in training data, right? The pattern is something like okay, and there's another class. These are the two class I want to separate. Okay, so if we'll have a very deep neural network, right, it will have a very good accuracy, no doubt it will have a very good accuracy, but that accuracy it will have in training data, and getting a very good accuracy means fitting this functions very well, right? So what it will have is, it will try to create some decision boundary, something like this, something like this, right?
Yeah.
Yeah, so this is what we would like to avoid. So what network is doing is, instead of generalizing the pattern, it is trying to mug up the pattern. It has fit this function so hard that if any point, if in real case scenario, if some point comes here, right, some point comes here, it will say it is a, it, this particular point will go to category of red points.
Mm.
So what we would like is, we would like to like our function to generalize the data instead of mugging up it. So ideally, we would be looking for some function like this, something like this. It's okay if we do some misclassifications in case of training data. Our goal is not to maximize or have the best performance of model in training data. What we want is our model should perform well in case of test data. So the model will be only able to perform good in case in test data if instead of remembering the pattern, if it understands. Maybe in training data, you see these points, these boundary points, they are the exceptions. So we do not want to, take in account those exceptions. Are you able to
Okay,
understand?
so I am understanding your point, but I want to understand like with some more example which you can tell, like, because the way you have drawn the graph, that is making me feel that, oh, this is like a very static graph now. It's
Wait, wait.
not even dynamic where it is moving around, because remember, right, these complex graph is where our other functions help us. In the beginning you said,
Yep.
but now it looks like you're again going back to the same simple graphs where the decision boundary is
No,
very
no.
static.
Wait, wait, wait. Let me clear your doubt. Okay. I'll do some more board work and this thing will get clear. Let me draw some input output relationship. Okay. I am having two classes here. Okay. One is the green class. The other is the red class. This green class I'm denoting by circles. Now I'm having another class, red class. It is something like this. First of all, tell me, is it linearly separable point or non-linearly separable point?
This is non-linear.
Yes, non-linear. Okay. Now, if I want to, segregate. So this is my training data, first of all. Okay. Now I want to build a classifier that segregate this red and green, right? And if so obviously this is not possible to do with perceptron, sigmoid neuron, or single layer sigmoid neuron, right? In this case, we have to use neural network, right? Now, what will happen if you're using a big neural network with lots of with a lot of neuron in it? It will draw some decision boundary, something like this. Will have some decision boundary. No. It need not to be like this only. The only point which I'm trying to make here is, right, it will have some decision boundary like this.
Yeah.
Still, in this case, you are misclassifying this point, right? So it will have
Yes.
even more complicated shape. But the intention you understood, right? It will have a very irregular shape of decision boundary that will try to fit the data too well, such that your accuracy in case of training data will be maximum, right? This is what neural network will try to do. Now, what I'm trying to say is the point which I'm having here, this may be a noise point also. In the real data, definitely you'll have noise point also. So here what we are doing is, instead of generalizing the pattern, we are overfitting the data, right? So in this
So
case,
you're saying that the points which are like crossing over here and there,
yes,
they could be noise. They could
yes,
not be like exceptions.
yes, there could be
Okay.
exceptions. Maybe because if suppose you are doing a time series problem, maybe the sensor that time there was some malfunction sensor was doing, or maybe there was some irregularity in data because of which you are seeing those exceptions. So we are changing the R pattern to fit those exceptions also. So that is what we should not do. What will happen is, although your model will perform very good in case of training data, but in actual test data, when you will get a real data, this type of functions may not do well in case of test data, right? Because I'm trying to fit noise also,
Yeah. Okay.
right? So this problem is called overfitting.
Because you're taking these exceptional cases, and
Yes.
that is why we are saying it's overfitting.
Yes, yes. I'm creating a very, very complex decision boundary which may not cater all points in general.
But why do you say that it is? I mean, I understand it's overfitting,
Mhm.
but it's good, right? Then I mean, if it is able to make these corner cases also
Yeah,
take care of corner cases, so what's the harm?
yeah. See, it is good. It is good if you look from the training data perspective. But our goal is not to have a good performance on training data only. We want to have better performance in test data also. So what will happen in real life cases if some green point is here, some green point, let's say uh, some green point is here, right? So
Mm.
you'll see that this green point is in very much proximity to actual cluster, but it will be classified as red because all the points which are in this side, they all are classified as red, and all these points, they will be classified as green.
So saying misclassification can happen.
Yeah, misclassification will happen when the test data will be given to you. So this point will get misclassified, right? Whereas if you,
But misclassification can happen even in if it is generalized, right?
yes, it
Because
is.
if your graph is the way you showed,
Mhm.
then there will be these exceptional cases, so they will be misclassified.
Yes, yes, that is also possible. But as a so forget about model for now. If
Okay.
just from like human eye, if you'll see this, to which particular cluster you will assign this point, green or red?
To green.
Why? Because it is more closer to green, right?
Yeah. Yeah.
Similarly, if I ask you this point, this test point, uh, this somewhere, let me put here, yeah, somewhere here, this, to which cluster you'll try to put this point, red
To
or green?
green.
Yes, because it is
Actually,
more, because it is
yeah, it is
closer
more
to
closer to
green.
green.
Yeah, but
Yes.
actually what model will do is model will wait. Yeah, model will also say it is a green. So let's take another example. Some point, let's say you have another point, let's say here. This is a green point. To which cluster you will try to put without looking this decision boundary? If I'll
To
just remove
green.
to green, but model will say that this is a red because the nearby just 2 point, those two were red,
Yeah.
right? So you understand what is happening. We want to mimic the human process, but this model has learned this process in a too hard way, that instead of generalizing it is mimicking the pattern. It is just you know hard coded the pattern. That is what we do not want.
Okay. Okay. So what I have understood so far, you're saying that because it is such a complex function,
Yes.
and in that particular training it happened, but say in future, other
Hmm.
data set that is coming,
Yes.
most likely it may not be always like that, and it will just end up doing this overfitting, and then it will end up misclassifying stuff, even
Correct.
though the data is, say, pretty uniform, where most likely it will be very simple. That
Yes.
is why this overfitting is causing us some problem,
Yes.
right?
Yes. Yes.
Okay.
Just because of this 2 point, we will not make our decision that this green point should be classified as red, right? Because they're just two.
Yeah.
These two red point can be noise also,
Yeah.
right? So ideally, what we want is, instead of this, hard coding the functions, it should generalize it well. So
Right.
our model should be intelligent enough to say that since there are only 2 points here, I should not make this functions this complicated. Rather, I should here just I can ignore those two functions. Let that two point get misclassified in training data, but the model should know that in test cases it will make the correct predictions for not many other points,
Okay.
right?
Yeah.
So yeah, so this overfitting concept you understood, right?
Yeah.
There's another concept called underfitting. So underfitting is what? Underfitting is just opposite of overfitting. in overfitting, what we are saying that the model has learned too well that it has perfectly able to segregate all the training points, but in test cases it is not able to perform well. Whereas in underfitting, the model has not able to identify pattern itself because we are using a too simple model. For example, if you'll use here instead of neural network, if you'll use here some perceptron model, right? So perceptron,
Yeah.
so what perceptron model will do is perceptron model will try to draw some line, something like this, which is a too easy function,
Yeah.
right? So this is called underfitting. So as a data scientist, what we should keep our aim is we should have some sweet spot between this overfitting and underfitting. The model
Okay.
should not draw a very complex function. Neither the model should draw a very simple function. It should be somewhere in between these two, right? And this
Yeah.
is called bias variance trade-off in machine learning.
What is called bias variance?
Bias variance trade-off means identifying the sweet spot between this underfitting and overfitting. So
Okay.
what we are doing is we are doing a trade-off, right? We are playing between underfitting and overfitting,
Okay.
right? So this is called bias variance trade-off.
No, when you say this is called, you mean finding out
Finding,
those points.
yes.
Like what is by BVT? Is it like some number?
No, it's not a number. It's it's more like a process. Finding the
Okay.
optimal sweet spot between underfitting and overfitting.
Okay. So it's a process.
Yes, you can say that it's a process.
Okay.
Okay. Yeah. Now what happens is this overfitting. So the chances that you will overfit data, it's very much depending upon the number of learning parameter you have. If suppose the model or algorithm which you are using, if it is having too much of learning parameters, right? In that case, the chances of overfitting the data is high, because we have seen that as we have gradually increased the number of learning parameters, our model was learning to understand, fit the complex function. If you'll recall, in case of MP neuron, we had just only one learning parameter, that was B, and it was able to learn very simple functions. Then we moved to perceptron. The number of learning parameter increased from 1 to 2, weights and biases, and then we moved toward neural network, and we saw drastic improvement because we had lots and lots of learning parameters. So although as we increase the number of learning parameters, we can fit any complicated functions, but the chances of overfitting is also high when we are using large number of learning parameters,
Okay.
right? So that is sometimes becomes a problem with feed-forward network, because in feed-forward network, if suppose you are using a large number of layers, large number of neurons, in that case you will have some problem called overfitting, right? Because there are a lot of learning parameters, right? So this is one drawback of feed-forward network.
Okay.
Okay, all right. Okay, let me clear this. Yeah. Now this point we covered. The next point is the other drawback is loss of vanishing gradient. So if you recall, in the previous class we saw the chain rule, right? How we backpropagate the gradient from our output layer to the respective weight. So this chain can be very long. So sometimes what happens is, if the chain is very long, if you are using a very deep neural network, by the time the gradient which reaches to the weight which is closer to input layer, it almost becomes zero, right? So if suppose this is my network, this network is very high, is very dense. Like this, I'm having total 100 number of neurons, and ultimately I'm having one output neurons, right? and these all are interconnected. Like this you have. Okay, so what happens is we back propagate that gradient, right, from our output layer to subsequent layer. If I want to update this weight, I need to back propagate that thing gradient, right? So this chain sometimes it's become too large that by the time this weight receives gradient, it almost becomes zero. And we know that if the gradient becomes zero, obviously weight won't be getting updated, because if this del L by del weight, if that becomes zero, obviously we'll not have any factor to subtract, and our weight will not get updated. So this problem is called loss of vanishing gradient, or simply it is called vanishing gradient problem.
But does that actually happen when this chain becomes too long? It almost becomes zero.
Yes, it happens, and this is one of the major problem of it. This will not happen if the network is shallow. It will have only 4 or 5 layers. Definitely, it will not happen. But if you think about a network which is having hundreds and hundreds of layers, this becomes a significant problem, because if we have to back propagate from that means you have to bring that gradient from nth layer to the first layer.
Yeah.
Right. So in that case, this vanishing gradient problem becomes a significant one, and you'll see that your weights will not getting update, and the learning process becomes stagnant.
Okay.
Right. So these two are the major drawbacks we have in case of feed forward network. Right. This is a very common interview questions. If you've understood it well, then one more.
What they may ask in interview, that explain what happens, like some of the issues of feed forward network. So we have to tell the.
Yes.
Okay.
Yep. Because see, what people think is neural network is a one-stop solution. People think that with a neural network they can achieve anything. What they don't know is, even with a neural network also there are certain pitfalls, and we should be aware of those pitfalls. Right. Okay. So this left us with another question, and that this question we need to ask to ourselves: can we have some other kind of network other than feed forward network, which has the same level of capability to capture the non-linearity and data, but on the same time it should have lesser number of learning parameters? Because by now we have understood that more the number of learning parameters, higher the chance of overfitting, and overfitting is a problem that we want to avoid in any kind of machine learning problem. Right.
Okay.
So this has given rise to another kind of network, which is called convolution neural network, CNN. Right. And this paradigm has done a remarkable job for image problems. Right. But before we jump into CNN part, I would like you to attempt these questions and let me know your answer. So the following is advantage of CNN over DNN. So CNN stands for convolution neural network, DNN stands for deep neural network or feed forward network.
The second one?
Reduced complexity of model leading faster convergence. No, that is not an answer. What made you think option second?
I thought that's what I understood. It means that the graph that you explained, right, that it's complex, the graph, and we want to make it simpler. So that sentence made me feel that it refers to that. But then it could be the first one then.
Yeah, the first one is the correct answer. See,
Okay.
reduced complexity, with reduced complexity, what I mean is your architecture should be strong enough to generate complex functions, right? So in terms of generating the complex functions, we do not want to reduce complexity. Rather, what we want to focus is we should have all the capability that feed forward network is having. It's just that the number of learning parameters should be less.
Okay.
What is the answer for question 2? Deep neural network are prone to overfitting due to large number of parameters. True or false?
True.
Yeah, it's true. Is everyone clear on this part?
Yes.
Okay. Now let us formally jump to the topic of convolution neural network, right? So this entire convolution neural network is depending upon convolution operations. And first of all, I would like to hear your opinion, whether you have came across with this term in your college studies or even after that, because I
mean
had
CNN?
convolution operations.
No.
Okay, because in my undergrad course, I had one entire subject on this digital signal processing. So that course is extensively dealing with convolution operation. No worries. Okay, so it's good that you're not really aware of this convolution operation, because it would have created a lot of confusion. So it's good that we are all like empty jar in this point. So whatever I want to fit, I can fit into that. Okay, so we will be understanding this convolution operations from deep learning perspective. Do not go with the literal meaning of it. The literal meaning of it is somewhat different, but we'll focus from deep learning perspective. Okay, so in the previous class also I told that an image is nothing but it's a matrix, right? So for now, just understand that a matrix we are having, which is 2 dimensions. Okay, so you can think it as a grayscale image. Okay, and each of the element is representing 1 pixel value of image. Okay, now I'm having a kernel. So kernel is nothing but you can think kernel as a matrix of weight. Okay, so in terms of CNN or convolution neural network, whenever we say kernel, it means that it is a matrix of weights. Okay, so if this is my image, this is my input image, and these are the pixel values I'm having. This is my kernel. W, X, Y, Z are the weights, right? If I want to perform a convolution operation, right, how do I perform a convolution operation? Is first of all, I have to superimpose these kernel over this input image, right? So I'm just, you can think it as I'm superimposing my kernel over this input image and perform the convolution operation. So convolution operation is nothing, it's very similar to dot product. So what will happen is this A will be multiplied by this W, right? And this B will be multiplied with X, E will be multiplied by Y, and F will be multiplied by Z. Okay, and we take the weighted sum of it. So now this A will be replaced by this value, which is nothing but A into B plus W, B into X, E plus E into Y, and F into Z.
So those 4 values are the summation of those 4 values, the product of them is considered as one value, and that is like output.
Yes, yes. So this
Okay.
A will be replaced by this value, right? Now what I'll do is I'll just simply slide my kernel horizontally by 1 step. So now just think that now this is how we are superimposing our kernel. Okay. Now again, this B will be multiplied by with W, C will be multiplied with X, F will be multiplied by Y, and Z will be multiplied by Z. Okay. And again, we'll take the weighted sum of it, and now B will be replaced by this value. Okay. So what we are trying to do here, understanding that part is more important. We are replacing the pixel value by the weighted sum of their neighborhood pixel, right?
When you say weighted sum,
Yeah.
what is that weighted? Weighted is that the kernel values are the weights that are being applied to those
Yes.
neighboring. Okay.
Yes. So in a way, what I'm doing, I'm doing averaging of my pixel value, right?
Yeah. You
So
mean the
that,
neighboring pixel values?
yes, yes, right. So that is precisely meant by saying convolution operations in CNN. So you'll see that in every operations, in every layers will have some kernel. So if you recall, when we did the hands-on operations, I showed you something kernel also. We created a kernel there in some functions, and I told that I'll tell you about the kernel later on. So this is
Yeah.
what the kernel means. There we created a matrix of 3 cross 3, right? So similarly, so this is a kernel of 2 cross 2. You could have created a kernel of 3 cross 3 also. So in that case, the superimposition would have looked like something like this. Right?
How much? 3 cross 3. Yeah.
Yeah, 3 cross 3.
So
Right.
one question now, Shishir. So the way you are moving the kernel, right, by 1 pixel each. So in this particular case, looks like it will be 1, 2, 3, 4, 5, 6, right? Total 6. There will be total 6 outputs.
No. There will be only one output. Wait, let me do this board work. So this is my input image, first of all. This is my image. This is my image matrix, okay? And let's say that I'm having A, B, C, D, E, F, G, H, I, J. Okay. Now, if I'm having a kernel of 3 cross 3, okay, this is my 3 cross 3 kernel, right?
Yeah.
I'm having, let's say all of my weights are 1. Okay. So what I'll do, first of all, I'll superimpose this kernel over this place. Right?
Yep.
This A will be replaced by what? This A will be replaced by all the elements, right, which are in this matrix, because my weight is 1. A plus,
Yeah. So the A will be equal to A plus B plus C plus F plus G plus H all the way till M.
yes, all the way till M, right? So now,
Yeah.
after performing this one convolution operation, this A is updated by this number.
Yeah.
Right? So one convolution operation will update only one value. Now once
No, that I got. But see, then this kernel will move, shift by, right? One by
window,
1 pixel value, it will shift.
yes, now this will look something like this.
Yeah. So then that is the second output.
Yeah, that is the second output. And again, now there will be only one update. This D will be replaced by similarly the summation of all the elements which are in this box.
Yeah. So I'm asking how many times it will move. So now it is moving 1, 2, then again it will move, right? And that
Yeah.
is final move.
Yeah,
Third move, it cannot move beyond third move, right?
yes, it cannot move beyond third move. So you might be thinking that in that case, this E and D will not get updated, right?
Yeah.
Yeah. So that, so in order to make sure that all this value get updates, we do padding. So there is a concept of padding where what we do is we impute some zero value, some extra value after this. So what I'll do is, if I have to do padding here, I'll extend this matrix and I'll put some zero value. Right? So if now zero value is there, I can slide my kernel even beyond this point, and you'll see that this D and E value will also get updated.
But how will they get updated when that is 0? It will be multiplied by whatever value is there and it will still be 0.
No, it won't be still be zero. So if I have to update this E thing, right?
Yeah.
I'll place my kernel like this. Sorry, I'll place my kernel like this.
Yeah.
So this E will be replaced by what? E plus
Oh.
J plus
J plus. Oh yeah. So it will update. It will change.
Yeah,
Okay.
it will change. Although here elements is 0, but still these two elements are there, no?
Yeah. So after it is done, then it will go 1 pixel value down, right? It will start from F.
Yes.
Okay.
First of all, it will cover all the pixel value all the way from left to right, and then this window will slide to this part. Now 1
Yeah.
pixel down, right? So similarly, you have to apply convolution operations on each of the pixels,
Got it.
right? So if you recall in the hands-on session, we saw the convolution layer, right?
Yeah.
We saw the padding layer. So what that padding layer was doing, it was putting that extra zero so that you can perform convolution operation even at the element which are at these positions.
So what is so padding is adding those zeros. What is convolution? Convolution is this kernel thing.
Yeah, convolution is
Kernel is convolution.
Yes, this operation is called convolution, right? Replacing this value, updating this a value by the weighted average of its by its neighborhood pixels.
Okay, got it.
Okay. Yeah. And you know, knowingly or unknowingly, we have been using these operations since very long. If you have worked with some, you know, image processing software, some photo editor, those photo editor use these kernels very extensively. Okay, so if
Who use it?
a photo editing software.
Oh, okay.
Okay, so some of the real life case scenarios where you actually find this convolution operation is when you want to do some blur operation if you want to perform, right? So in that case, they will be using this kernel one by